Thank you very much for the introduction, Christian. Well, there were no questions yet, so we continue the warming up. Maybe I create some, but we'll see. I will show you two examples which we made in task group B2B in order to evaluate the impact of the new Eurocode. These examples were made before to assess the impact of the first Eurocode compared to well, all the former national codes. The first example will be a pile designed from static load tests. These examples are, well, very simplified. We took out all the complexity in order to show how all partial safety factors and correlations factor work and where to find them. So we have an example, board piles. So these are replacement piles, 1.2 meter diameter, 15 meters long, carrying a building with specific characteristic permanent vertical load, characteristic variable vertical load. And we have here in the diagram the load test results. From these four load test results, we determine the ultimate bearing capacity at 10% displacement. So that's 120 millimeters, and I already give you the answers. What is important, as you saw in the presentation of Christian, is that we evaluate the bearing capacity looking at the mean value and looking at the minimum value. The mean value of these four outcomes is 2.04 meganewton, as the minimum value is substantially lower, 1.73 meganewton. Would we have evaluated this using the current Eurocode for four load tests? We would find a correlation factor by which we should divide the mean value of 1.1 and a correlation factor on the minimum value of 1.0. This did not change in the new Eurocode, so we find the same correlation factors. However, it's stated in the notes to the tables that these correlation factors are also based on a coefficient of variation of 12%. This implies you should do something with your data set. However, this is not the outcome that came to the code by now. In calculation, this will be different. If we look at the model factor and the partial safety factor, we see that the partial safety factor on replacement piles, as on all type of piles for load testing, is 1.1. There's not so much variation in this partial safety factor because you take out all uncertainty by testing this pile. In a calculation model, when you have a pile type that's well, heavily influenced by execution, you have to implement it in your calculation model. If you test a pile that's already made, you have this uncertainty actually covered by testing. So that's why all partial safety factors are here most probably the same. Same counts for the model factor. As Christian already showed, and I will do it again, static load tests have a model factor of 1.0 because, well, what you see is what you get, most probably. where other types of load tests are subject to an evaluation to come to a bearing capacity. And as you can see, there's only one verification case, of which I will show you the impact, and that's mostly the impact of what you all have to do in order to come to a conclusion on bearing capacity, if it's sufficient or not. Because what you see here is, well, the various design approaches, and for sure each country had its own choice of methods by using the old Eurocode already. However, there were some countries you saw on the map that were free to use one of these three, and then outcomes are heavily dispersed. Now it's all clear. We just use verification case 1, and we come to a resistance of 1.57 based on the minimum value and the resistance, partial safety factor on resistance, and the model factor that should be applied. Here it looks like the outcome for resistance is much more than as per the former Eurocode, but I will show you later on that the difference is actually not so much. When we look at the verification cases that we used to have, this is an old table because here you see a design case, but it's just in the wording. If we look at design case or verification case 1, we see the partial factor on permanent load is 1.35, whereas the partial factor on variable actions is 1.5. If we go to consequence class 2, we don't have to multiply these factors by more than 1. And we go to the action side, from representative to design actions. Here you see that by using the old Eurocode design approach 1 combination C2 would have given us a design action of 10.2, because there are lower partial safety factors on the action side than we would have should be using according to this new Eurocode, where the outcome will be 12.9 even, what is actually the same outcome as we would have had using design case 1 combination 1 or design approach 2. Probably this will cause questions. If we look at the final outcome then, comparing the action and the resistance side, the current Eurocode would have given us a foundation of 9 piles, whereas the proposed second generation Eurocode also gives us 9 piles, however with other values. So conclusions with regards to this simplified example is that the new code specifies which design case to follow, so you don't have to evaluate multiple design approaches, and even more important, because those choices were already made by countries, but it's easier to compare between countries, because otherwise when you are working in another jurisdiction you always think, oh, factors and actions, should I be so low, should I be so high? This is now all taken care of. What's new is the model factor for the accuracy of the chosen design model for the tests. And the new correlation factors which are proposed give slightly more conservative characteristic values by more than 5 piles. And the last thing, the note that the correlation factors are based on coefficient of variation implies that you should do something, at least think of it, when you have dispersed outcomes of your tests or tests that are not close by but on very large distances. To compare this to a pile design from ground test results, we take the same case with the same calculated bearing capacities per pile, only this time we assume that these bearing capacities were derived calculating them from CPT profiles. So we get the same mean value and the same minimum value. Here the new table looks much more complex. If we would have been looking at the current Eurocode, we find a correlation factor of 1.31 that we should divide the mean value with, or 1.2 on the minimum value. As were the first thing we find out when we use the proposed new Eurocode, is that our coefficient of variation for these data set of 4 piles is 30%, 1% higher than is acceptable using the value for the mean, which is given in this table. So we should split this data set, and because we did not give you more information, we assume that all CPTs are in one straight line, and we see with which data set. I thought it was me, but it's not me. We assume that these CPTs are all in one straight line, and if we take only 1, 2, and 3, our coefficient of variation will be 11%, so just below 12. So we can continue with this data set, and with the other data set is only CPT4. And here we find new correlation factors, 1.33 on the mean for 3 tests and 1.23 on the minimum value. And again,
take it out.
Quiet. Okay, and again the minimum value is normative here, giving a representative value of the resistance of 1.41. We will not go further into the result of CPT4. What we see here for the partial safety factor and the model factor is that we use different tables. This is also...
Shut it down. We can hear you.
But it is not this mic. They're all the other mics. Yeah, the system. Thank you. For the model pile method, you see it's also the case that for all types of piles we have the same partial safety factors. In the simplified example, we look at total resistance. Normally from a CPT you would have calculated base capacity and shaft capacity, but It's just to show you, to find the table. You see it also has a quite high table number. It's easy to get lost between the tables for using ground model calculation method, model pile calculation method, or pile testing even. We saw that in the task group, and probably we'll hear some more about it later on. And here you see also the model factor for the ground model as well as the model pile method, which we are using here. And the model factor for the model pile method is dependent on what ground tests you do. In this case, we choose CPT tests, which gives you a model factor of 1.1. Actually the same exercise to come to a design resistance because of the other model factor. We have slightly lower outcome, and the same table again for verification case 1, which we already saw in the partial safety factor table. Here we have the same outcomes, obviously. So we go quickly to the last slide, where we see that actually same situation using a ground model method. It's a little more complex because of the coefficient of variation. It's stated that you have to use it evaluating your data set of outcomes for various test results. Current code would have given a foundation on 11 piles, whereas the proposed new Eurocode gives you 12 piles. And actually the same conclusions, but in the case of using a ground model method, you have to do something with this coefficient of variation. But what if we would have used the ground model method? Here I also presented the tables for the ground model method, where you can see you have a partial safety factor that's different for full displacement, partial displacement, or replacement piles. Also when you look at base and shaft capacity separately. And you see that if you don't do pile testing, all the uncertainty which is not covered by a correlation factor is actually covered in the model factor. So I will point it out because not everybody looks immediately at the bottom left. If we would have used a ground model and we don't do any testing, we would have had the same foundation, 16 piles. Whereas testing on the job site would bring it back to 12 again. Important to notice. And in my personal opinion, if you have to do static load testing, better start with it, because then it would have been 9 piles. And this is where the code will help you. That's all I had to say. Christian, a very nice picture.